All right, my friends, we're on to this last one, and this last one is probably, in my eyes, maybe the most challenging one out of all the ones that we've gone over. And quite frankly, this is a question that I think would be really hard if it showed up on your AP exam. But remember, we can always try to get a few points here and there, right? That's kind of the goal. We try to get a few points here and there to help us make sense of this. So with that being said, let us go ahead and get started. So the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differential function r on time t, where t is measured in minutes. It's a lot of stuff there. From 0 to 12, the graph of r is concave down. Okay, very interesting. So they're also letting us know from 0 to 12, the graph of r is concave down. The table above gives selected values of the rate of change r prime of t, the derivative. We kind of know that because it's r prime, of the radius of the balloon over the time interval. The radius of the balloon is 30 feet when t equals 5. Okay. The volume of a sphere of radius r is given by this function. Okay, very interesting. Estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Okay. All right, that's pretty tough, but we do know tangent line approximation, right? That means y minus y1 is equal to m x minus x1. Well, at t equals 5, right? Using the tangent line at t equals 5, right? So now with that being said, now we know it's going to be with t, so t minus t1, there it is. And we know at t equals 5, the balloon is 30 feet. So that's pretty nice. So we know y minus 30 is equal to m t minus 5, right? Well, how do we get m? We're going to get m by taking the derivative and plugging the values at 5. Well, guess what? We already know the derivative because that's the table. It's the derivative, and at 5 it's 2. Beautiful. So now I know this is y minus 30 is equal to 2 t minus 5. So now we have the tangent line. Here it is. We now have the tangent line approximation, but then the problem did say estimate the radius of the balloon when t equals 5.4. So all we have to do now is plug in 5.4 minus 5 into our function, and let's go ahead and solve this out. 5.4 minus 5 is 0.4. 2 times 0.4 is going to be 0.8 at 30. Y is equal to 30.8. Very good. And because we're talking about the radius is kind of like the position function, and we know it's feet per minute. Well, that radius, what is the length on the radius? It's feet. So 3.80 feet. So the radius of the balloon at t equals 5.4 is 30.8 feet. Beautiful. Okay. Now it's asking us or let me backtrack. Is your estimate greater than or less than the true value? Is your estimate greater than or less than the true value? Well, keep in mind, this is why the problem told us that the original graph from 0 to 12 is concave down. This is a really bad concave down graph, but right, we are concave down. So our tangent line approximation at 5, right, theoretically, our tangent line approximation at 5 would be something like this, and it's 5.4, right, which would be above that. So that kind of lets us know that the tangent line approximation should be greater. Right, if this is at 5, it should be greater. And even no matter where you kind of draw this at, since it's concave down, this approximation will always be greater. You can see that, right? So let's go ahead and answer that. So let me go ahead and just write this down below here. Since the graph of r is concave down on the interval 5 to 5.4. This is all we care about, right? We know it's concave down from 0 to 12, but most importantly, we only care about from 5 to 5.4, right? Because the 5 would be our location, right, where we're making our tangent line, and the 5.4 would be the approximation, which would like either be here, or if this was 5, it would be right here, right? So since we're concave down on this interval here, we now know that the estimate is greater than the true value of the radius of the balloon. Boom. Okay, good. Whew. All right, let's go to part B. And I did accidentally put these two together really close, so I know it doesn't look as appealing, but that's okay. Part B, find the rate of change of the volume of the balloon with respect to time when t equals 5. All right, this is something we have to be really mindful of, right? And we've gone through this quite a bit. Find the rate of change, that means derivative. So we know we need to take the derivative of the volume of the balloon with respect to time. Well, do we already know the volume equation? Well, yeah, they gave us this volume. V is equal to 4 over 3 pi times r to the third here. And they want us to find the derivative of this with respect to time. Well, we don't have any t's here, right? There's no, this isn't in terms of t. So that tells us that we're going to have to do implicit differentiation, right? That's kind of be the key, very similar to the ones we did in class. So I like to put parentheses around my r. That way I'm reminded of the chain rule. So if I take the derivative of v, the derivative of volume, that would be dv over dt, because it's with respect to time and it's not with respect to t right now, right? It's v equals 4 over 3 pi r to the third power. So that's very important for us to keep in mind there. All right, so let us go ahead and continue on. Okay. 4 over 3 pi. I'm just writing down what we know. What's the derivative of r to the third? Well, this is going to be 3r squared, right? We ignore the inside, bring 3 down, subtract by 1. What's the derivative of the inside? The derivative of r is not going to be 1. Remember, this is with respect to time, so this is dr over dt. All right, and we're trying to find the rate of change of the volume, right? We're trying to find dv dt. So let's think about this real quick as we kind of work through. The 3's cancel, and I get dv over dt is equal to 4 pi r squared dr dt. Okay. Well, do we have any information about dr dt and r squared? Do we have any information about that? That's the question. Well, think about it. And I gave you a moment to try to see if you could look it over. When t equals 5, well, this is radius. Do we know when t is equal to 5, do we know what the radius is? Well, let me read the question and let me see if I find it. Oh, there it is. The radius of the balloon is 30 feet. When t equals 5. Ah, that tells me this will be 4 pi. This is going to be 30 squared. Okay. Now, what's dr dt? What is dr dt? So this is 30. Well, when t equals 5, do I know what r prime is? At 5? Do I know what r prime of 5 is? Well, that's the table right here. At 5, r prime is 2. So we also know dr dt is 2. Now we just got to multiply this out. 30 squared times 2 times 4. We'll get 7,200 pi. And again, I know this, but you can do it. They obviously want you to. And it does say indicate units of measure. And that could be kind of tough. Well, your units of measure are going to be right here. What is the units of your radius? Well, the units of your radius is feet. And we have feet squared times dr, which is feet per minute. So this is going to be feet to the third power divided by dt, which is just minutes. And that would be the solution to our problem. Very tricky, very tricky, because we had to, quite frankly, make sense when t equals 5, our radius is 30, and the dr dt, the derivative, the rate that the radius is changing when t equals 5 is actually given to us by the table values. Very good. All right, let us begin question number 5. Now, I took the time before the video to just go ahead and make a quick sketch. So, and I should have maybe waited, but we're using a right Riemann sum with the 5 sub-intervals indicated by the data to approximate this. Using correct units, explain the meaning of this, right? So, I went ahead and plotted my points. I feel confident that you can do that. And then we're going to do a right Riemann sum, which means we start from the right. So, we start from the right. There it is. Starting from the right, boom, 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 and boom, right? Here is our function right there. Again, you don't need to connect dots, but I did, so you could see that it's an under approximation in case that was to ever come up in this problem. But you didn't have to do it. This is 2, this is 3, this is 2. This is 7, 8, 9, 10, 11, 4, 1. What is my y values? This is 0.5. This is 0.6. This is 1.2. This is 2. And then this is 4, right? So now we are in business to kind of get started. So I'll start with my first rectangle. 4 times 2 plus 2 times 3 plus 1.2 times 2 plus 0.6 times 4 plus 0.5 times 1. There it is. Good. So I got that right there. We are in business. This is approximately going to become 19.3 feet. Okay. How did I know this was feet? Well, let's use unit conversions. R prime is feet per minute multiplied by minute. And minutes cancel and we're left with feet. So we're getting back to position, right? The position, well, in this case, the radius. So how do we explain this? Well, let's begin from 0 to 12. R prime of t dt means, well, we're talking about the radius. This gave us the rate that the radius is changing. So taking the antiderivative and getting feet is just going to tell me that means the change in radius in feet from t equals 0 to t equals 12 is in minutes? Minutes, right? Don't want to make that mistake and put hours or something like that. So this means the change in radius in feet from t equals 0 to t equals 12, right? And that's how we can go ahead and write that down. And we are in business, right? We're good. We got that there and we're solid. Wonderful. All right, let's go ahead and go to part D and take a moment to read it. Is your approximation in part C greater than or less than that right there? Is your approximation in part C greater than or less than? Well, if we went back up here, first of all, we can already tell that our approximation is going to be an under. It's going to be less than, right? You can look at the graph. We're missing area. And we can even add the fact that the graph of ours is concave down. So we could say, since the graph of R is concave down, and I used a right Riemann sum, and R prime of t is decreasing, my approximation is less than this integral, which is an under approximation, right? It's going to be less than. So we can kind of add all that down there. We know r is concave down, which is just something that was added. We also know r prime is decreasing. We know we use the right Riemann sum. Therefore, my approximation, I guess I might add my approximation, which was 19.3 feet, is less than this value right there, less than that right there. Good. Beautiful. And that kind of concludes that question there. Pretty tough nonetheless, but hopefully you feel better.